Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
The two things we're going to do first and foremost, give you a quick introduction to some RF concepts that are very critical for you to do prior to just jumping in and doing to the design. And the second part of this is going to be common layout practices, and I'm going to introduce to you Gary Gaddie, one of our team members and a very experienced RF engineer. So let's talk about the two things we got to do before we ever get anything over to the PCB design. And that is the layer stack up and the materials. Now, most of us, if we've done PCBs in the past prior to doing RF, we've always taken the approach of, I'll deal with the layer stack later on. And I want to minimize things to the nth degree because, hey, there's a cost involved with more and more layers, right? Want to try to do it in 2 layers, can't do it in 2, we'll try to do it in 4. We really have to go to 6. You've kind of got the idea about that. We can't do that in RF or even in high-speed design. Okay, so it's like a house. We can't just kind of build a house ad hoc. Some people can do it, but for the fact of the matter is, if you're going to build a house, you really got to build something that's got a design, it's got a plan, it's got an architecture to it. And in the PCB world, it's really no different, especially in the high RF microwave range, and that is the layer stack up. So we have to move away from this ad hoc method of, I'll deal with the layer stack up layer. We've got to actually deal with it before we even push the net list over to the PCB side. And the big question is why? Well, it's all about the impedance. And when Gary gives his presentation today, you're going to hear that time and time again. Everything deals with the impedance. And the amazing part about the impedance is you may be looking at this very ugly equation over here, and it's not something you got to solve by hand. But if you look at this close enough, you can extract 4 factors that deal with impedance. One of them is the trace height. And guess what? Trace height is copper weight. Copper weight all out with the manufacturer. What else do you have over here? You've got a dielectric constant. That's the materials that you call out to the manufacturer as well. Okay? Most of the time we use FR4, but we're going to talk about materials here in a few minutes because that has an impact on the dielectric constant. And then also trace to plane distance. This is another thing we call out to the manufacturer as well. So the fact of the matter is, 3 of the 4 factors that create the impedance is something we've got to deal with the manufacturer. And that has to happen up front. So why is that? Because normally when we do a board, let's just say a regular board, not super high speed, there's no RF on it, we usually default to FR4. In fact, if you don't even call out a material, the manufacturer is probably going to default to FR4. It's the most common material used on the planet for printed circuit boards, and they know how to work with that stuff in their processes, right? But over here, when we're dealing with RF, we're dealing with a different creature. And we've got to realize that the impedance plays a major role. And as a matter of fact, most of the time, we already know the impedance. These are going to be like 50 ohms, or it's going to be something that's like 100 ohms for differential pair. So the 3 of the 4 factors is something we've got to call up front. And then you say, well, what do I get to control in the RF domain? Well, really, the only thing you get to control is the width. However, since we already know the impedance and we already know what we're going to give to the manufacturer, the only thing that's left is the trace width, which is going to be dictated to by all these things that we just gave to the manufacturer. So you can see how important it is for us to do all of these things up front. We can't just ad hoc this along the way like we may have done in the past when we were just working with FR4. All right, so layer stack is really important. Let's talk about materials because there's a dielectric constant in there, and you have control of the dielectric constant. And again, the most common material, FR4, it's got a permittivity of 4.7. There's a lot of other materials out there. The list is in dozens. There's an entire specification that shows literally dozens of different types of materials that are out there that the IPC knows about. There's ones that are coming out all the time by these other different companies over there, and they probably have different dielectrics that may make the traces a little bit thinner, which, hey, we want to get it smaller, right, so we can get it onto a smaller board. But we have to be really careful about that because the manufacturing processes are set up for FR4 for the most part. And if we decide to pick another material and we don't discuss this with our manufacturer up front, there's two things we can expect. We're actually adding risk, and some of that risk is pretty severe. Number one, we may drive up the cost substantially on the board. What may have only taken, you know, a typical turn may be now, hey, it's going to take us 3 times as long. It's slowing down our processes. We're getting a lot of fallout on this thing. We're going to have to charge more for this. And then the worst part is they come back altogether and say, hey, look, we can't manufacture this. This stuff does not run through our processes, and either change your design or find another manufacturer who might be able to help you out. So be very careful about the materials that you choose. And so our point about what I want to drive home here is that before you start putting anything onto your PCB, you can work the schematic to your heart's content, get it through review, get your bill of materials done, make sure your libraries are clean. But before you start doing any placement or layout on the PCB, your layer stack up and your materials must be known, and that means you've got to have that conversation with your manufacturer. And you're saying, that's great, my manufacturer doesn't do this. Well, you get two points of information. First and foremost, if you're looking for an RF, high-speed, even microwave type of manufacturer, you'll see our contact list at the end. Feel free to contact your sales representative, and we can point you in the right direction. Secondly, if you're going to go out on you're going to look around and see who's out there and what they can do, these are the questions you want to ask. Number one, what percentage of work is done, their work is done in RF and microwave? So if they're saying like, yeah, we've done 1 or 2 before, and 98% of their work or 100% of their work has pretty much been in traditional rigid PCBs with FR4, that's probably not the best company to go with. You don't want to be their guinea pig. Again, it's about risk mitigation. The materials that they work with, and in particular, what materials are they stocking? If they're stocking the material, that means they're using the material, and that's a good thing. If you're calling them up and, well, we could order that for you, you want to go a little bit deeper into, well, have you ever worked with it before? Because if they haven't worked with it, you have a tremendous risk there, because it may come to a certain point in the process saying, you know what, we just can't manufacture this. For example, some of these materials may work great for 2 and 4 layers, but beyond 4 layers, they can't register it. It's got too much stretch to it, and so as a result, they can't register it properly beyond 4 layers. Okay. Another aspect of it is what tolerances this material can handle. So all too often, we try to stuff everything onto a single board. So we have a massive BGA that's got 3 mil clearances, or pardon me, 3 mil traces, and we got an RF with a 19 mil trace on it. Hey, if that material is got certain tolerances, it may just make it impossible to do the digital. They may say, hey, look, with the tolerances we got over here, the best we can do is a 5 mil trace as it's stretching because the registrations are very difficult to work with. All right, another aspect of it, can they do additive copper? Now you're saying additive copper, where's that coming from? Now, additive copper, the concept's been around for years. We generally don't do additive copper because it delaminates very easily. So most of the time, if you're familiar with the manufacturing process, you actually take a copper sheet, you do a lithography on it, you FA the material. However, there are companies out there, one particular company that recently did a presentation at IPC San Diego here, did one on additive copper. It's a company out of Carlsbad, California called eService, and they're being very aggressive about getting their technology manufacturers here in the United States in particular. Because they've perfected it. They've got additive copper working, and they were bold enough to suggest by the end of 2015 that will be a very common practice to use, which is a great thing. So ask them if they're doing additive copper, because it gives you more control and more, especially over the tolerances of what you're working with. Lastly, are they resharpening the bits? If you're going to do RF design or anything with high precision, you want them to use a new bit every time they spent one. A lot of these companies money, they'll try to sharpen it. On some of the slower designs, yeah, fine, they can reuse it. But keep in mind that anytime you sharpen something, you're removing material, and there's no guarantee that the symmetry is going to be there from as the original bit was created. So it's best that you actually have them not reuse a bit, to basically use a new bit every time. And if that's an additive cost, so be it. At least that helps with your yield. So those are the kind of questions that you want to ask. The last thing I'll mention too, I know we're all trying to save that extra penny over here, but when it comes to RF design, you have to pay for the quality. So it's one of those things where either you pay for the quality up front or you're going to pay for it by doing it over again. So with that, you've heard me ramble on. Let's get on to the good stuff over here. I'd like to introduce to you Gary Gaddie. So Gary has got over 34 years experience in the PCB design industry, and he started off with the hand tape method. So he's watched this whole industry really grow over the years, which is really great to meet someone who's got such a history behind him. In addition to this, he also has done analog and digital design. So he's not just a layout guy. He's also done the circuit design as well. His industry spanned from military through commercial, medical, and everything in between. He's got quite a repertoire of stories. I'd love to collect them all sometime because it's really cool, the stories that he's mentioned to me as we were putting this presentation together. And he is involved with the IPC, and in particular, he is the CID+. So with that, I'm going to introduce to you Gary Gaddie. And I'll turn the presentation to you, Gary, at this point. And Gary, at this point, is taking over the presentation, and he'll be putting up the slides here in just a moment.
Hold on. Okay, you should be seeing, again, the same 9 dots connects. Hi, everybody. My name is Gary Gaddie. I'm very excited about the first webinar for myself, and I'm excited to bring some of the knowledge that I've gained over the years to you guys, and excited to be here. So with that, Paul mentioned that I am a IPC certified CID plus designer. And what that means is that I've taken the advanced CID course. I would encourage everybody to get involved with IPC, learn about their specifications, find out what they can do for you, how to use them, and we'll be going more into that as we continue along. I'm going to give you examples of materials and stuff that's specified by IPC. So when you're certified to CID+, that means you not only understand the basic techniques for designing and laying out circuit boards, but you also understand the manufacturing side of it, the material side, the signals, signal integrity portion of it, and it's just really lends credibility to your overall knowledge of the process. So let's see, I'll move on to the next slide. This is just a quick blurb on a specification sheet from IPC. It's just generic in that it's only FR4, it's /21, it's a pretty common material, so I just want to give an example of that. And, you know, I'd encourage everybody to learn about IPC, learn about the specifications, and try to work with your vendors to find out what's their common usage of these materials. And if you discover that you want to use exotic materials, make sure you clear it with them and make sure that they not only stock this stuff, because one of the things you'll find as you move through the more exotic materials is there are a lot of things to know about it, such as moisture absorption. A lot of these people will not actually store this, will not stock this material because of the absorption of moisture and special environments that they need to be located in. So with that, I'd like to move on to the idea of stack-ups. Stack-ups are critical. You should understand your stack-up before you begin your design. One of the things that is critical in designing RF, a lot of you will already know this, but grounding techniques are critical. If you do not have a good grounding and shielding scheme, and it all starts with the original stack-up. So you can see in this is a generic boilerplate stack-up for an 8-layer board where layer 2 is ground, layer 3 is another signal located next to the sequential layer of layer 4. So, and then One thing I'd like to make sure you guys understand today is the fact that you've got to create balanced construction. The reasons are numerous, but suffice it to say that if you don't create a balanced board, your board manufacturer is not going to want to design or build that board for you. So start with the stack up. This next slide that I've got is more of a specific stack up. And this where, and I'm going to be showcasing a design that I'm working on right now for another customer, wherein they've got dissimilar materials. That's not uncommon, believe it or not. And here we're looking at a standard FR4. It's one of the top line high temperature materials. You can see it's called a HR370. That's specific, and you can see also up here that it's R4350. And what that means, the first number is the thickness of the dielectric, and the R4350 is a Rogers high performance RF material. So I am only showing this just to show you how specific you can be in your stack ups. And with that, I want to go on to a material call out that you should have on the face of your board. This is a depiction of a note that would go with the previous stack up I just showed you, where you have not only standard glass fiber FR4, but also a PTFE ceramic material. And there you see the IPC spec 4103. You'll notice the difference between 4101s and 4103s. So again, some additional IPC specs about copper foil, and we can help you guys streamline your notes such that you get what you plan on. And I personally can make information available to you to help get your notes. All too often, you'd be surprised how often a board will stop because of a boilerplate note that has no consideration in your current design. So just thought I'd throw that out there. We'll be doing more of that in subsequent presentations that I hope to be part of. So looking forward to bringing you guys a little closer to my neck of the woods. And with that, I think we should start talking about impedance. Obviously, that's one of the main goals of all RF microwave designs, is maintaining an impedance across your circuit. This should be desired. The desired impedance should always be on the face of the drawing. You'll notice a note 17 that we're referring to here. That's a specific note that says that, hey, you guys need to look at the dielectric constants, you need to look at the impedance charts, and you need to build the board according to that. So this is a representation for single-ended 50 ohms. There's circuits on layer 1 that are referencing. You need to tell them the reference layer, and you need to tell them the nominal width that you've designed into the circuit. This second one showcases a layer 3 trace that needs to be referenced to not only layer 2 but also layer 4, its impedance, and the nominal trace width that you designed into it. Next slide shows you an impedance chart for differential. Impedance chart for differential equations, where you've solved these equations, you've designed the circuit board, and now you want to make that data readily available on the face of your drawings to your vendor, so that there's no secrets, there's nothing that doesn't exist in your existing documentation that's hidden from view, and everybody, including the sales team, the guys that quote those boards, everything is out front. So I would always encourage you guys to put this information on the face of your fabrication drawings. So likewise, these are various layers and the reference layers. Not only does it spell the nominal trace width out, in this case in inches, as well as the nominal spacing to ground, and we'll get more into that as we look through our next slide. So with all the mentioning of impedance and impedance calculations, I would like to show you guys one of the tools that I use that's free and off the shelf. It's available from this, and we can help again make links available so that you can download this for yourself. This just happens to be one board manufacturer, and you'll notice that we start out in a microstrip situation. These different kinds of callouts that you see in the area that I'm highlighting focus on the different types of impedance-controlled circuits. The second one that I want to show you is the strip line. Oftentimes you'll have to transit from the surface of your board to internal layers to get to another part of your circuit. And so you can see here where the circuit is embedded between two ground planes. The most common one that I'm used to using is the coplanar waveguide. And what this is commonly you will pour ground on the outside of your boards, and you'll have your impedance. Let's go ahead and just pump a couple of numbers in here, and I'll show you how this thing works. I think that this is set up for, let me hit enter. Okay, we're getting exactly 49 ohms with standard FR4 material. So assuming that you're going to use a non-exotic material, you can expect to get 49 ohms, and then there's a tolerance involved, obviously, with this, and that should also be on the face of your drawing. So let's take a moment and drop down to a more exotic material and watch the numbers as they change. So here we're going to Rogers 4350. You'll notice the impedance changed from 49 ohms to 56 ohms. So to achieve your, this is an advanced material, so therefore you get less loss in your basic circuit board. And let's see with that. So I would encourage everybody to use solvers like this. They're typically available from your board vendor. If they don't provide that, then we can certainly help you. You'll notice a lot of other tabs here. It's really good for a lot of stuff. So I really like this software. It's free, and I've used more exotic calculators, but this is a kind of from the root pretty basic solver. So I use this a lot. I use it on every design. And I use it for stuff even when there is no impedance. I just want to know what a 10 mil trace is going to be. You know, typically you'll design even digital circuits to 50 ohms. It's a good default value to have for most traces. So with that, let's move on to the next slide. We talked a minute about vias and how you have to transit from one layer of the board to the other layer of the board. And this is a download that it was part of a class that I took down in San Diego, where you're trying to control not only EMI, but you want to control the impedance as the signal transits from one layer of the board to another layer of the board. And one of the things we're going to talk about right now is the clearance or anti-pad involved in a via. And this happens to be a study of the different anti-pads that are used and how they affect your circuit. So with that, I'd like to go to the next slide. This is a chart that shows the loss in decibels over a frequency range. You can see there's a great deviance, and these numbers on the right represent the anti-pads for a via that is the same size. So by altering that anti-pad, the distance away from your ground to the actual via structure is used on the right here. You can see it actually has a tremendous effect on the performance. So the next slide shows the results of these equations. And you can see here where they found the actual sweet spot for the via anti-pad, in this case 0.6 millimeters. It's performing exact, and this is not black magic. It's actual rocket science. So I would encourage you guys to be familiar with your via structures, and in future, I would like to get more into this subject. But for now, I'd like to move on to some depictions of vias that and how you should use them. So this slide depicts a digital circuit. It's performing at a fairly low rate, and the purpose of this slide is to show you that it is crucial that anytime you transit from one layer of a board, in this case the blue color represents the bottom side of the board. It's the digital part of an RF circuit, and in a minute I'll be showing you a different part of this same board that's the RF section. So it's very common that you're going to have not only digital, but power supplies and RF circuits all on the same board. They do compete with one another, and as Paul mentioned, you may have a 3-mil line in one fine line BGA area where you've got big giant traces in another part of your board. So we'll get into copper thickness a little later in the talk. But here I want to make sure that you understand what I'm showing, and that is that you have a via located in close proximity to any transit vias. And what this allows the circuit to do is have a perfect return path, or an increased return path that is going to allow the circuit to not become noisy. If you do not have these there, you will have a loss in performance. So moving on to the next slide. This is part of the RF circuit for the same board I just showed you. These happen to be through-hole vias that go all the way through the board and transit to an internal layer. You can see that they are grouped, surrounded by ground vias to provide a good return path for this signal. This is a 50 ohm high-speed signal. I think this guy is running at about 8 gigahertz at this point in the design, and you can see that shielding is critical. You need to put as many vias as is possible without being ridiculous in your board and allow it to follow along the path of the circuit. So that's the purpose of this slide. The next slide that I'm going to show you is this is a typical SMA in-launch connector where we've got 50 ohms coming into the board. This is where this might run off to an antenna or other board that provides an RF signal onto the board. What I'm showing here, and the purpose of this slide, is to show you how the green area that you see here is a negative image, and it's basically this block is going to prevent ground from residing right underneath the surface mount land area for the center conductor of an SMA connector. And the purpose of the ground being forced away from this area is to maintain the 50 ohms that is desirable. Obviously, this trace right here is 50 ohms. You've already done your calculations. You understand that ground is, X amount of mils or millimeters away. And but as you transit to the larger feature on your board, you should adjust the ground such that it is accommodating the 50 ohms that's desired. You also, by not including this in your designs, you will increase the capacitance, affecting the overall circuit, and not getting the 50 ohms that you had planned on. So that's the purpose of this slide. And so one of the things that is also extremely critical is grounding and shielding on your board. What I'm going to actually do here is launch a tool that has a circuit board design. This is an RF circuit that runs at about, again, 8 gigahertz. pretty speedy when it gets over here at the end of the circuit. Not all of it's running at that speed. But the purpose of this, me launching this tool, is to show you a typical application where you'll sequester all the power supplies away from all the RF circuits in different portions of the circuits that have, you know, gain, attenuators, little power supplies that actually through inductors and so forth. So you can see along the top here that I've got a group of power supplies. These are switching power supplies that are extremely noisy. In no way do you ever want to put these circuits adjacent to your RF circuit. So placement is key there, and this just happens to be a good depiction of shielding. This the area that you see here is copper that's going to come into contact with the enclosure both on the top and bottom of the board. And you will actually open up the copper interface to allow this to come in a close proximity to the copper. So you can see there's quite a bit of work involved in doing the mechanical on this type of design where you have, and it's quite common that you'll have power supplies and A to D converters and in this case a USB interface circuit all on the same board. So another thing that you might notice is all these little circuits in blue. This is the far side of the board, the red color being the top of the board or near side of the board. These are little power supplies that have a very limited usage. And let me select net. And you'll notice that these circuits are localized. Wait, here's an actual the input power here on that's highlighted, and then the output voltage that I'm trying to highlight right now. So it's always a good idea to take your power supplies and take other noisy circuits and put them on the opposite sides of your boards. If you can do that, if you've got the luxury of the room to do that. In this case, this board's definitely going to be successful the first time out. We've allowed the room, and you know, it's not often that you get, I was told, make the board any size you need. So in this case, I took advantage of that and made plenty of room in between the various circuits. And you know, it's not that, this is more or less a proof of concept board that proves out that the circuit will work. And I'm looking for success the first time out for this customer. So with that, I would encourage you to talk to your mechanical people, work with a mechanical engineer that's closely to make sure you don't design in something right here that can't be made or that's not going to work for them because of one reason or another. It's often very common that you go back and forth and back and forth and back and forth between mechanical and electrical engineering. So work with the people that you have. Again, we can help you, but these are all considerations that need to be taken into effect. You should know your overall board limits and number of layers and stuff like that before you ever really design the board. And so moving on. One of the things that is common in the industry, and I know some people will not even understand what I'm trying to show here. Let's see, where am I? Okay, I'll move this down. This is a back drilled via, and it's something that most people are not familiar with. So let's say that you've got a components on both sides of your board. This is a depiction for an 8-layer board. You've got a RF line that you're trying to get from the top of the board down to, let's say, layer 3. And then it continues on from there to get to a different part of your board. You'd have ground on layer 2 and 4, and then you'd have a bunch of other circuits on these sequential or these subsequent layers, layer 5 through 8. The ground bounce that's in, so the bounce of a signal, a very high-speed signal from the time it's used on layer 3 until it gets down here to layer 3 on a typical through-hole application, the signal will actually bounce back on itself and create a harmonic and create a noise jitter on a via that is not back drilled like this. Now, there is partial drills and blind and buried vias that we're going to get into on some future stuff that I hope to speak about. So this is just to make you guys aware that there is the availability for removal. They often will do this for hot pad removal when you've got a solid sheet of copper that you're going to use for sinking heat out of an RF design. Some of these amplifiers will sink several watts of dissipation, forcing you to have intimate contact with the back of the board. So this is a good way of solving the fact that, hey, I'm going to have a solid piece of aluminum on the back of this board. I don't want any hot vias touching that board, and I don't want to worry about signals coming in contact with the enclosure. Just kind of throwing this out here to tease you guys, and hope you'll come back for more information. And you know, I'd like to stress the fact that I learn every day. There's never a day that I don't get up hungry for more information and more technology. And you know, I'm excited about learning every day. And as we know, this is a fast-moving industry. New stuff's available, faster components are available, higher speed materials, and as Paul mentioned, new processes such as additive copper that force us to stay on top of the latest technologies. I personally am really interested in physics, and I'd actually recommend everybody goes to a website called phys.org.com, and some of the latest technologies and materials and showcases for all physics are located over there. I spend a couple hours perusing that data every day, so I'm really interested in that stuff. So that happens to be one of the things that I feel is of benefit to me, and I personally enjoy it. So one of the things we talked about was IPC. So I would encourage everybody to find out about IPC and IPC certification. If you're designing circuit boards, you might think about getting IPC certification. It's readily available in most parts of the country. In fact, locally, there's at least 3 or 4 opportunities a year to take their classes and get their certification. You know, you want to start out with the regular CID class, and hopefully you'll see the benefit and move on to CID Plus. That's going to make you familiar with all the processes involved in circuits and how they perform, how they're built, signal integrity, how to solve issues. I know we've got speakers that are coming to you that talk a lot about high-speed digital design, and I don't want to encroach on their material. So they are all tied together. You know, high-speed circuits are high-speed circuits, and solving the impedance issues and the grounding issues are critical for good performance of any circuit. And it can be anything, even down to you know, 400 megahertz power supplies that are generating huge amounts of noise into your ground planes. Let's say, for example, one of these devices here. You'll notice that most of these are closed loop. They provide ground underneath the component, and I would encourage everybody, if you're using power supplies, download the data sheets for them. They oftentimes will make available to you right in that specification the good practice or desired practice of location and of components and how to make a good circuit, and they'll show a good depiction there. It's critical that power supplies are your worst offender when it comes to generating noise into a circuit. There's also stuff that we'll be talking about later, like groups of vias and how to avoid large voided areas in your ground planes. And I think probably other people will be talking about that. I know I will be in the future.